Okay, so hi everyone. My name is Uiseop Eom, a research engineer from a research group called ML2 in a semiconductor company in South Korea called KC. Today I'm going to be talking about optimizing iree to match llama C++, um, an introduction to an optimization journey for newbies through the benchmark journey. So hopefully this might help to newbies like me who are just getting into LLVM projects such as MLIR. So first of all, what is iree? Iree is a project that is a retargetable MLIR-based compiler for ML programs. They take various front-end inputs such as PyTorch, JAX, ONX, and such on, and also they execute on different backends, such as x86 CPUs, ARM CPUs, and GPUs, and so on. So basically, they provide a runtime and a compiler system that builds bytecodes that runs on those runtimes. So they're helpful for running various ML programs on edge devices and on heterogeneous device environments. So the reason why our team kind of looked into iree first as a testbed for studying and understanding MLIR and LLVM in general was that iree is basically MLIR native and it's an end-to-end compiler stack. And also we thought that it would be a right scale for newcomers, and that includes lots of abstractions for hardwares as well. So basically it's an end-to-end stack that can get you your hands dirty on the MLIR compiler stacks in general. So we started benchmarking this iree project, which is based on MLIR, on Tiny Llama. At first we started out with Llama 3.18b instruct, but later on we decided on to using Tiny Llama. So, basically it was for faster iterations because our main goal was to work on targeting on edge devices, because our research group is more focused on robotics and also edge devices as well. So, so if there's anyone who's trying to benchmark on large language models and edge devices, always use Tiny Llama instead of Llama 3.1, since it's better for the fast iteration. So the basic benchmark results that we got from the iree project was that per token it took 23 seconds per token, and compared to Llama C++, it took 84 milliseconds. It had like more than 200 speed differences. And so this kind of started a benchmark journey, which included lots of MLIR and getting your hands dirty on MLIR optimizations. So before that, we realized it took a lot of debugging into the MLIR stack inside iree, and I realized that the CPU and kernel profiling didn't help much. Well, first of all, basically it was because the iree project itself is binded, uses Python binding, and the C++ code stack is hidden behind the binding. So the CPU profiling and the kernel profiling weren't much helping due to because the C++ stack was kind of hidden behind the bindings. And instead, using Tracy, a C++ framework, a frame profiler kind of helped a lot. So using Tracy to debug the slowest frame, and then using the MLIR print.ir after all option, which is basically an MLIR optimization option, but which is also which iree also has, kind of helped to finding the MLIRs and the basic blocks that kind of hindered the slowing parts. And using actually the diffing the intermediate MLIR files was the only way to actually see what happened onto the MLIR between the optimizations, which was kind of hard because you have to see all the text messages. But yeah, so I guess that's what you can do as a newbie for looking into MLIR debuggings. And one thing is that, especially in ML programs, huge MLIR constants in tensor operations always deteriorates debugging experience because, it basically bloats up the MLIR file up to 4 gigabytes, 8 gigabytes, and more on. So one tip for anyone who's new to MLIR is to always use dense resource element attribute to reduce the IR size, which is basically sorting out the tensor constants outside the MLIR files. And Iree project also had its own attribute inside their own flow dialect, which is called named parameter attribute. So I'm pretty sure that if you're looking into MLIR optimizations or MLIR files, they'll probably have an attribute, a function that you can use to source out the tensors. As like a conclusion, but at the end, none of the MLIR optimizations that I worked on really kind of helped to reduce the inference time, except the actually working on the inference code instead of working on the MLIR compilation. So the KV cache with page attention really helped, and it managed us to reduce the token time, which was 23 seconds per token, millisecond per token, to 421 milliseconds per token. So this is one of the tracy results that I got, and the left one was before adding the inference optimizations, and the right one is after adding the optimizations. You can actually already see that the most function that uses up the most time is always a waiting function. So you can probably see that if I had got my hands on Tracy first, I would have found out that that there was a bottleneck on the memory instead of a compilation optimization errors. So some takeaways from my journey was that first of all, observe before optimize. So which if I had done, I would have saved up much more time. And the code and prefill time is always different when using ML programs and compilers, because the code always works out with gem matrix multiplication, while prefill works on gem matrix multiplication, while decode works more on GMV matrix multiplication. So use that. Always keep that in mind if you're working with any ML compilers, and also keep the IR small at all times so that you can work, that you can keep the debugging going on. All right. So that's it for the talk. I have much more details on a poster session that I have after this talk. So I hope to see you there as well. All right. Thank you. That's all.